Hi guys, I just wanted to make a video here because there were a couple of example problems that were in your class packet for today that we didn't quite get to during class. So I wanted to just go through and model how to solve these example problems so that you have them to refer back to and to help you out with understanding this week's content. So here is our second example problem. So in a particular right triangle, the base x is 12 inches and the height y is 5 inches. The base is shrinking at a rate of 2 inches per second, and the height is increasing at a rate of 3 inches per second. Determine the rate at which the area is changing. Okay, so first thing that I want to do to tackle this problem is draw myself a picture. So I know this is a right triangle. And I know that the base x is 12 inches, right? The base x is 12 inches and the height y is 5 inches. So we know that we're going to have this hypotenuse h. And we don't know what that h is yet. We'll find out in a second. Let's see, what else do we know? We see that the base is shrinking at a rate of 2 inches per second. Ooh, so let me set up my haves and my needs here. Right, so I have and I need, well, y equals 5 inches, x equals 12 inches. We know that the base is shrinking at a rate of 2 inches per second. So the base x over time is shrinking. So over time, the change in the base over time, dx dt, well, it's shrinking at a rate of 2 inches per second. Shrinking tells me that it's getting smaller, AKA this is going to actually be a -2 inches per second. Whereas the height is increasing, at a rate of 3 inches per second. So the height, the change in the height, dy dt, is positive 3 inches per second because it's getting longer. Now, like we said, we need to figure out, okay, what is the hypotenuse? What's the length of the hypotenuse? And we also need to determine the rate at which the area is changing. So the change in area over time, dA dt. Okay. Well, to figure out the length of the hypotenuse, well, we can just use Pythagoras, right? X squared plus y squared equals h squared. Now you might notice this is a special right triangle because we've got legs of 5 and 12. So you can use Pythagoras to check this out here, to double check. But we also know that the hypotenuse, this is a 5, 12, 13 right triangle. So the hypotenuse is 13 inches. This is a special right triangle, but again, you can use the Pythagorean theorem to double check that. Okay, now we want to know what is dA dt? What is the change in area over time? Well, to figure out the change in area, we first have to write ourselves an equation for the area itself, right? Well, what's the area of a triangle? Area equals 1/2 base times height, or in this case, x times y. 1/2 x times y. So now to find dA dt, I need to differentiate each side of this equation with respect to time. We're just differentiating with respect to time. So on the left, we have dA dt, which is what we're looking for. That's wonderful. Now, x, the length of the base, and y, the length of the height, are both changing over time. They are both functions of time. X and y are both functions. So I know we're going to need to use the chain rule, but also I see that it's x times y, a function times another function. So I know that I'm going to have to use the product rule as well. So let's take this one step at a time. So product rule, first times derivative second plus second times derivative first. Okay, first times derivative second. Well, the first function is that 1/2 x times derivative of the second. So times derivative of y. Well, y is a function of time. So the derivative of y is dy over dt. Now plus second derivative first. So plus the second function, y, times the derivative of 1/2 x. Well, okay, I can put that 1/2 coefficient. And then again, x is a function of time. So the derivative of x is dx dt. I'm going to rearrange this slightly just to make it a little bit prettier. I'm going to factor a 1/2 out of each term. So I get x times dy dt plus y times dx dt. And now, taking a look back up at my haves and my needs, well, I have x, I have dy dt, I have y, I have dx dt. I've got everything I need in order to solve. So dA dt equals 1/2 times 5 times 3 plus 5. Oh goodness, not 5. That should be a 12. Sorry, this should be 12 times 3 plus 5 times -2. All right, this just requires a bit of simplification here. So dA dt equals 1/2 times 36 minus 10. 36 minus 10 is 26. Half of 26 is 13. dA dt equals 13. And what are my units? We're looking at a change in area over time. So the area is going to be measured in square inches, right? Because these legs are measured in inches. So area is measured in square inches. And yeah, the changes in the legs are measured in inches per second. So I'll use seconds again here. The change in area over time, dA dt, is 13 inches squared per second. Awesome. Let's take a look at one more problem altogether. Example number 3, a spherical balloon is being filled in such a way that the surface area is increasing at a rate of 20 centimeters per second when the radius is 2 meters. At what rate is the radius changing when the radius is 2 meters? Okay, as always, let's make our haves and needs chart. What do we have? What do we need? Okay, well, the surface area is increasing at a rate of 20 centimeters squared per second. So the surface area is changing over time. So dSA, for surface area, is changing over time, over dt. And that is at a rate of 20 centimeters squared per second. What else do we have? We have that the radius is 2 meters. Radius is 2 meters. Now, what are we looking for? What do we need? At what rate is the radius changing? Well, at what rate is the radius changing? That's asking for dr dt, the change in the radius over time. Cool. So we know what we have, we know what we need. Now, as you may know or not, this is going to be on your reference sheet on any test. It's not something that you have to have memorized, but it is true that the surface area of a sphere is 4 pi r squared. Again, that's not something that you need to have memorized. It will be on your reference sheet, but that is what the equation that we're gonna need in order to solve this problem. Surface area is 4 pi r squared. Okay, so now we need to differentiate both sides of this equation with respect to time. We differentiate with respect to time because both the radius and the surface area are changing as time passes. So over here on the left, we have dSA over dt. And let's see, over here, we again have to use the chain rule, like our example from class. So if we take the derivative of the outside, well, we need to take our exponent, put it out front. I'm just gonna go ahead and multiply that 2 times 4 to get 8 pi. Decrease the exponent by 1, so r. And then the derivative of the inside is dr dt. Now here's something interesting. Right now, the derivative of the surface area is isolated. However, we're looking for the derivative of the radius. So I'm going to actually divide both sides by 8 pi r just to isolate dr dt. So this will cancel out. And I'll just switch the sides to make it a little bit prettier. Dr dt equals the derivative of the surface area over time divided by 8 pi r. And now we plug in our known values. It's just algebra from here on out. Dr dt equals 20 divided by 8 pi times 2. So this is equal to 20 over 16 pi. 20 and 16 are both divisible by 4. Let's go ahead and make that simplification. 5 over 4 pi. I'm going to leave it just in terms of pi. That's fine. But I do need to add my units. So at what rate is the radius changing when the radius is 2 meters? Okay, so I'm looking for the rate of change of the radius. Well, the radius is measured in meters. And we're looking for its rate of change over time. Time is measured in seconds. So it's 5 over 4 pi meters per second is our final answer. All right. Well, we made it through 2 more example problems. I hope those help you out. And I hope that you get a chance to take a look at this video before we dive into class tomorrow, because we're going to continue working on some more related rates problems. And I, for one, am very excited. I look forward to seeing all of you very soon. Bye.